Today we're looking at the first topic of Unit 4 of the specification, which is capacitance. So we're looking at what capacitors actually are and what they do and the equations associated with them. I've included a specification from the WJEC. It goes over 2 slides, which is quite lengthy, and there are 2 practical tasks with this as well. Today we're going to be looking at the first 3 parts of the specification, the structure of a capacitor and what it actually does, how it performs at a particle level, and then looking at the first equation, which actually provides the definition of capacitance. So a little bit of background on capacitance. As you can see from the top, capacitance is actually the ability of an object to hold electrical charge. And over time, we've developed devices that are better at this than naturally occurring or other devices. The unit for capacitance is the farad, which is named after Michael Faraday because he pioneered the early work on capacitors and capacitance. So looking at the first part of the specification then, what a capacitor actually is. We have a picture here to show what capacitors look like, and you can see they come in a variety of forms. They're made from a variety of materials as well, but in terms of getting an idea of how they actually function, it's these 2 here that we're going to focus on, which is why I've enlarged this one in the bottom corner. Now you can actually see the structure of it here. It's lots and lots of metal plates running parallel to each other. That is what we find inside a capacitor. Inside the more cylinder ones, these would be coiled inside them. So you have one plate running around another, because that saves space then when you're actually putting these onto a circuit board, so you can make devices much, much smaller. The symbol for a capacitor actually gives us a far better idea of what they're doing. So you can see here the wire going in, and then we have 2 parallel plates. Now in between that plate, in a traditional capacitor, you would either have air or nothing at all, a vacuum. So part B is looking at what actually happens when a capacitor is functioning. Now, with our 2 metal plates, it'd be fairly obvious that if they are just there, sat there, not connected to anything, that they would have electrons sat on them just because they're made of metal. And that it would be reasonable to assume that the amount of electrons per unit area would be the same for those, based on the idea that one plate would be made of the same material as the other. Strictly speaking, that's not always true, and it is possible to get different levels of charge and different levels of electrons on both plates. But within the confines of the specification, we can consider them to be balanced when they're uncharged. So when we actually apply a voltage across a capacitor, we do get a flow of current. Despite the fact that there's a gap between those plates, they're close enough that the charges on one plate can influence the charges on another, and therefore make them move, and that current continues to flow. So as those electrons flow around the circuit, we would get an excess of electrons on one plate, causing a negative charge. And that much bigger negative charge causes a repulsion on the other plate and forces the electrons off the other plate and down the wire. So the electrons move that way, giving this plate a positive charge. Now, it's really important to be able to talk about capacitors in terms of the correct terminology. It's really common to hear capacitors referred to as a store of charge, which technically is not true. If we look at the diagrams, we can see that although there's been a movement of charge, actually there is no more charge within the capacitor than there was at the beginning. So although the left-hand diagram shows it as being uncharged, and the right-hand diagram shows it as being charged, there's actually no net charge overall. It's not a storage of charge. And in fact, it stores electrical energy rather than charge. And when you're talking about it, it's important to use that terminology correctly. But moving on to part C, our definition of capacitance. We saw earlier on the slide with Michael Faraday, it talked about capacitance as being the amount of electrical charge for a given voltage. And that, in terms of the words, is enough to derive our definition. A better way of stating it would be the electrical charge stored per unit of potential difference. And you can see, looking at this, that if we go through that word incorrectly, we end up with charge divided by voltage. And that leads us to our first equation. So our capacitance is the charge divided by the voltage. Now, it's a fairly simple equation, but people do make mistakes with this. Okay, so we saw earlier capacitance being linked to Faraday. That is measured in farads, which is a capital F. A more likely term would be microfarads. Okay, so you'd need to use your data booklet or know that micro is times 10 to the minus 6. Where the confusion comes from is that Q, the total charge, is measured in coulombs, which is abbreviated to C, or very often as microcoulombs. And because we've got that unit as a C and the symbol as a C, people can make mistakes and enter data into the wrong space in their equation. And V is obviously our potential difference or voltage. Now, the WJC do like to link this to prior learning as well. So it's important to also remember that you've covered charge in Unit 1, where we looked at the definition for current as being the change in charge divided by the change in time. Or you should also know the definition of the amp, where 1 amp would be the equivalent of 1 coulomb of charge per second. So they can tie that in as well to lead you in other directions with the questions. So obviously once you've got the voltage and you've got the current, you could calculate the power or you could calculate the resistance as well. So they can extend these questions. So I will put a task sheet for you on Teams. There's only 4 questions looking at that first equation and linking it back to that definition for current as well. And I will post the answers for that with lesson 2. Good luck and message me if you have any issues.